All right, applied calculators, it is time for us to do the chain rule in reverse. If you haven't read the section, it's a good idea to read the section, but I'll try to teach it as if you haven't read the section. The chain rule is going to help us to do questions like this. Find the integral of 2x times x squared plus 3 to the third dx. There are a couple of ways to do this. One is to use algebra to expand those brackets, get some ridiculously long polynomial, and then use the power rule one term at a time. But we notice something. We notice that this is the integral of chicken nugget cubed, really, right? And we notice that this chicken nugget has a derivative hiding out somewhere else in the problem. This is the derivative of the nugget. And when that happens, good things follow. So here is what we do. We do a complete change of variable. We get rid of everything that smells like Rx, and we replace it with U. Well, what does that mean? We let U be x squared plus 3. I don't want to be x squared plus 3. It doesn't matter. We're going to let U be x squared plus 3. And then we're going to remember that the derivative of U is 2x, which means through a little bit of chicanery that we can replace 2x dx by du. And that's wonderful because this is u cubed, right? This part is u cubed. This part is the du. 2x dx is du. We have completely changed variable. Everything that smelled like Rx, we got rid of, and we replaced it with something that smells like U. So what do we do with this? Well, we do this the same way we would have done any other indefinite integral. We use the power rule on U cubed. We increase the power by 1 and divide by that new power, and it's a family of functions. So we don't give the answer in terms of u because the question was asked in terms of x. So we give the answer in terms of x by replacing the u with the thing that's u. This is the process known as U-Substitution. It allows us to do the chain rule backwards. It allows us to do the chain rule in reverse. I will demonstrate more. Find the integral of 3x squared times e to the x cubed dx. And we think to ourselves, this looks like an e to the chicken nugget. Like it looks like an e to the chicken nugget where the derivative of that nugget is hanging out right there. So what do? We let u be x cubed. And if u is x cubed, then the derivative of u is 3x squared. And so with a little bit of chicanery, 3x squared dx can be replaced by du. So what does that mean for this integral? Well, the 3x squared dx, that's du. E to the x cubed, well, x cubed is u. So we ask ourselves, has every vestige of our x been replaced? Yes, every vestige of our x now has u. So we can do this the way we did every other integral in the world. We need something whose derivative is e to the u. Well, the thing whose derivative is e to the u is e to the u. But we don't write e to the u, we write e to the u. We don't write e to the u, we write e to the thing that is equal to u but contains x's. So what are we figuring out? We're figuring out that things in brackets make good u's, powers of e make good u's, one other. Things in denominators make good u's, particularly because the thing in the denominator is a cubic and its derivative is quadratic. So things in denominators make for very good u's. And if the thing in the denominator is u, then the derivative of u is 3x squared plus 6x, which means that du with a little bit of chicanery is 3x squared plus 6x dx. What's the problem with that? The problem with that is that this is not that. Close, but not. Close, but not. So how do we talk about x squared plus 2x dx? Well, what's the relationship here? The thing we want is a third as big as the thing we've got. It's a third as big. Well, what does that mean for us? This stuff is 1/3 of du. This is u, and it's in a denominator. Now, what do we know about integrals? We know that constants that are multiplied can come right out. I don't have to worry about them, and I can just focus on what 1 over u's antiderivative is. So what's the thing whose derivative is 1 over u? Well, the thing whose derivative is 1 over u is the natural log of the absolute value of u. Now, we don't write u in the final answer. We write u in the final answer. And if you check yourself, you'll find out that the derivative of this thing here is that thing there. So I'll do a second video with more examples for those people who want a little bit more practice, but this is the main idea. We identify some part of the integrand as u, and we'll know that we're right if its derivative is hiding somewhere else in the problem. I'll bring a few more examples in another video. And if not, if you don't watch that, then know that I will see you in class and be glad.